I hope you can see my slides. I'm just going to flick through them. So I'm going to start here with the Big Bang. Now, we don't know what happened before the Big Bang. And in fact, the whole concept of before the Big Bang is a bit strange because time itself was started at the beginning of the universe. So it's impossible to even comprehend or understand that there was something before the Big Bang, because there wasn't even time before the Big Bang, and there certainly wasn't any space. So when people ask where did it start or what was before it, those are both kind of questions which are impossible to answer. And of course we can't measure it because there was nothing there. So I'm going back to a few milliseconds after the Big Bang itself, after the universe was created. And what we can measure from our telescopes looking deep into space is that it was an incredibly energetic time. And when I say energetic, it's just incredibly hot, hotter than you can possibly imagine. We're talking billions and billions. Well, look at this. It's 100 noctillion Kelvin, which that's basically, in those big numbers, you can think of that as centigrade. We're absolutely cooking. In fact, it's so hot that anytime the energy wants to kind of settle down into something like actually, naturally, if you've got that much energy in a concentration, it will drop into some form of matter because that's more stable and it's happy. But this is a bit like bubbling water. It's so hot that any condensation, any coming together of the water immediately reboils and burns back into energy again. So there's no mass, it's just pure energy. And that's it. But it only lasts like that for an absolute fraction of a second. Now, it was Einstein, this funny creature here, who came up with this amazing equation, which in very, very simple terms, just means that mass can turn into energy. And if you've got enough energy, you can turn that into mass. And the C there, which confuses everyone, is just a big number. It's technically 3 times 10 to the 8. So that's 300 million. So one bit of mass gives 1 kilogram of mass gives 300 million times 300 million joules of energy. So that's a massive amount of energy. And it works the other way around. So you need an incredibly huge amount of energy. If you've got that in a very concentrated space, then at the beginning of the universe, that starts to kind of like condense, just like water forms into droplets, the energy formed into mass. And we got the smallest and most simple mass possible, which brings me on to my next slide, which is this. Now, hopefully all of you will have met our friend hydrogen over here and our friend helium over here. Now, these are the two most simple atoms in the universe. But even these weren't formed at this point. When the universe expands. Now, if you've ever used after spray or deodorant or anything out of a spray can, you'll notice the end of it gets colder and colder the more you use it. And that's because when a gas expands, when something gets bigger, like anything gets bigger, it cools. It needs energies to have that expansion. And it gets the energy from the heat in the surrounding area. So as the universe expands, some of that energy turns into mass, and some of it also, the whole thing cools down. And that means the mass can stay as mass rather than reboiling off again into energy. So the simplest things we started to get were protons on their own, were electrons on their own, but it's still too hot for the electrons to kind of settle into their orbits around the nucleus. They'd like to be close to each other because they're oppositely charged, but even this doesn't happen. So we're in a situation which we call a plasma. Now, plasma is where you've got protons and neutrons, but they're not attached to any individual electrons. It's too hot. As soon as the electrons get too close, they kind of get excited again by all the energy and then bounce off and move around again. But these are the basis of the first 2 bits of mass that we have in the universe. Now, those who have studied anything to do with radioactivity or or even chemistry, you might have heard about a thing called an isotope. Now, hydrogen, the atom hydrogen, is made up of, well, the normal type is made up of 1 proton and 1 electron. And the normal name for that one is hydrogen. That's what we normally think of when we talk about hydrogen, but it's called protonium. That's its proper name. And another type of hydrogen, it's still hydrogen because all hydrogens, remember, have 1 proton. That's what makes it hydrogen. That's why it's called hydrogen. It's a code for saying 1 proton. So all isotopes of hydrogen have only 1 proton. So these all have 1 proton, but some of them are a bit fat. They've got more mass than they should have. So this one's got an extra neutron, and we call that deuterium. And this one here has got an extra 2 neutrons. So we call it tritium, a bit like tricycle, which means 3 wheels, 3 parts to the nucleus. Now, these are atoms because we've got a plus charge in the middle and 1 minus charge on the electrons. But again, we're not at this stage yet. We're still in a plasma. All of these are delocalized. They're not together anymore. But these are all forms of hydrogen that are formed right at the beginning. As soon as the universe cooled, we get these protons and neutrons. It cools a little bit more. The protons and neutrons can start to stick together again. And if we continue to cool, what will happen is any electrons out there in that massive plasma will start to drop into their orbits and start circling and making the very, very, very first atoms that you see here. So at the beginning of the universe, it was, I can't remember the exact numbers, but it's 90% plus were in the kind of hydrogen type. And we had a few of those heliums. Don't quote me on the 90%, I need to check that. But generally speaking, there was a lot more hydrogen than there was helium. And, well, these are particles, aren't they? And in space, if we go on to the next slide, this is what we get. We get these massive clouds. Now, this is not like a light photograph because you can't see hydrogen. It's a gas. But this is what was taken in the thermal, like infrared, that type of lens was used and telescope was used. And these gases block some of the light from the stars behind. And we can see on this picture here that we've got this massive cloud of basically hydrogen and a little bit of helium. And this is what we call a nebula. And you can think of it a bit like the place where stars are born. So right now, let's go back a little bit, let's just check we got it right. We've had the Big Bang. It's incredibly hot. It's expanded slightly. The universe is getting bigger very, very quickly. And as it gets bigger, the temperature starts to drop. It gets cooler and cooler. We're still billions of degrees, but it's getting cooler. And as it starts to get cooler, the energy can kind of condense into matter. And we get the starts of protons and neutrons and electrons. And it gets cooler as the universe gets bigger and bigger and bigger. And the protons start to stick to the neutrons. And then as it gets even bigger and even bigger, the electrons start to find their orbits and we get the first atoms appearing. Now, generally speaking, that's it. I'll just go back a slide here. Why don't we get bigger things like helium? Now, the challenge is, can you see that both of these protons have got positive charges? And these will naturally repel away from each other. So it's actually quite difficult to make bigger atoms. You need a lot of energy and things colliding together really, really fast for a plus to stick to another plus in the nucleus. So that's why most of them are hydrogen on their own. They don't want to hang out with another proton. Occasionally we get one. So we've got the situation, we've got the universe, we've got hydrogen, we've got helium, but we're not made of just hydrogen and helium. So where did all of the other elements come from? Our bodies are mainly carbon, mainly oxygen, some hydrogen, but we haven't got those yet in the universe. And how we get them comes down to the first stars. We're actually made of stardust. This is what we're made of. A bit of hydrogen and helium from the beginning of the universe and all the other elements that are made in stars. So as the universe expands, we get hydrogen and helium formed. That has its own gravity. Any matter has gravity. And so these hydrogen and helium particles have got tiny amounts of gravity, but which means they kind of hang out closer together. But of course, as more come closer together, you get a denser bit of space where there's more and more matter. And of course, that has its own gravity as well. And so that pulls in together, and it gets denser and denser and denser. It takes millions of years, if not billions of years. But slowly, slowly, we get this word called coalesce, which means the particles come together. And that gravity pulls even more in and more in and more in and more in. And just like water going down a plug hole, if you open the bath or let the water out of a sink, everything starts to come together and to start to spin. And this is the beginning, the first steps of a star being born. So here we are. Here's a picture. I hope you can see that. We've got this circling clouds of hydrogen and a little bit of helium, and they're being drawn in just as it goes water down a plug hole. It gets denser and denser in the center. And just like the opposite of releasing a spray can or pumping up a tire, it gets hot. So when you squash things, they get hot. And so it starts to glow, just like anything. If you heat up a bit of metal, eventually it will start to give out light. So it gets hotter and hotter and hotter. And of course, as it gets hotter and hotter and hotter, we get another plasma forming. The electrons are moved off the atoms. They're all excited and bounce around all over the place. And we've got this massive mix of electrons, the nucleus of hydrogen and the nucleus of helium. And we start to get this glowing disk. Now, at the beginning of the universe, these clouds were massive. I mean, billions and billions and billions of kilometers across. And so they made incredibly big stars. And big stars, eventually, when they start fusing, which is what I'm going to talk about next, they glow blue. And we can still see some of these stars out in the universe. We'll just get a telescope out, if it's powerful enough, or you can look out and you compare the different colors of stars. There's bluer ones, there's redder ones, there's yellowy ones, like our sun. They're all different colors. And that's all to do with their size. So this is a massive star. And when I say massive, I mean, well, it's at least 10 times bigger than our sun. And it could be up to 300 times bigger than our sun. I mean, these are enormous. Right. What happens? Why does it suddenly burst into life? Why do we get this incredible amount of heat and light and energy pouring out of stars? Well, it's not just the fact that they're hot. It's not like the squashing of the gases produces all that heat. We get this amazing thing called fusion. Now, fusion, if we go back up here again, remember these protons here, they really don't want to join up to each other because they've got the same charge, just like ends of a magnet. A north and a north really don't want to come together. Imagine them as magnets with Velcro, you know, a kind of sticky, gluey surface. So if they're anywhere near each other but not touching, they repel each other. But if they manage to touch, at that point, they will stick together. So how do we get them close enough to stick together before they get pushed apart again? Here we are. So here's our deuterium. Remember, that's just a normal hydrogen with one extra neutron. And here's tritium, again, hydrogen, but with this time it's got 2 extra neutrons. We need a massive amount of heat, thousands and thousands and thousands of millions of degrees centigrade, to get them moving, whizzing around really, 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 really quickly. And then we also need them really close together. But gravity does that for us. The gravity is squashing all of these things. Remember how big a star is. Remember how big our Earth is, how small that is, and how much gravity we feel. Well, the gases inside a star are under immense pressure from gravity. So not only are they incredibly hot, moving incredibly fast, but they're also forced close together. So eventually you'll get a situation where these two combine and crash with enough force to overcome that repulsion, and the surfaces touch and they stick together. And this is what happens at this stage here. We get deuterium and tritium, 2 types of hydrogen joining together, and which creates helium. Now, in this process, energy is released. Now, we're not going to go into detail on this because it gets very complicated very quickly. But in that reaction, the deuterium and the tritium, lose a tiny, 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 tiny part of mass. And that's turned into this pure energy that is given out. And that's what causes the star to glow with amazing power and amazing intensity for billions of years, while this reaction happens again and again and again. And in fact, our star's been doing it for about 5 billion years already. And we've still got we're only about halfway through. So it's got a huge resource of helium there to fuse through, to release all of this energy. And so we get this energy as heat and light, and we also get kicked out a really, really fast energetic neutron, which has got loads of kinetic energy again, which bashes into something else and gives out even more energy. Or maybe that neutron goes on and bashes into a normal isotope of hydrogen and turns that into deuterium. So that's where the energy of the sun comes from. And that, as I said, is the kind of main lifespan of the star is in this stage here. But of course, eventually, just like our star will, it will run out of hydrogen. Well, then it's got to do something else. If you can imagine, I'll go on to the next slide here. You've got gravity all the time, squashing and squishing and bringing everything together. But there's also this massive release of energy, like a massive explosion going on in the inside. These two forces are working against each other all of the time. If fusion starts to slow down, gravity squashes it more. So fusion speeds up, and so it pushes outwards again. And you get this balancing force, which gives us the shape of our stars, the shape of our sun, that that kind of globe-like shape that we have, the spherical shape that we have. But no more hydrogen, no more fusion. You get a sudden collapse of the center of the star. But then we can go back again, and we can imagine now that deuterium is not a deuterium, but it's a helium. So we've got two heliums now, and they're squashed together because the core has collapsed. There's even more gravity, so they're closer and closer and closer together. And there's enough pressure and enough energy for them to collide and stick together and release even more energy. And that stage is called a super red giant. And here it is. So this is how our sun won't ever be a super red giant, because it's not quite big enough. It will be a red giant, but the same kind of principles apply. So in the center, well, let's go from the outside. So we've got this hydrogen, which is so far away now from the center, there isn't enough gravity to cause it to fuse together. And it kind of drifts around quite happily around the outside of the star. As we go further in, helium are being slammed together under immense pressure. They combine together. Well, if we get one helium and another helium and we join them together, we've now got something with 4 protons in the center. Now, 4 protons in the center, can I remember the periodic table? What's the 4th one? It goes hydrogen, helium, lithium, beryllium. So we get in the form of beryllium is being formed. And again, this happens again, the closer and closer we get to the center of the star now, the more and more pressure there is, the more and more force pushing these things together. And we can keep fusing together all of the different elements that we see in our periodic table, all the way up to iron. And iron is the last thing that this star can fuse. Just so happens that iron in itself, that number of protons and neutrons, forms a really stable kind of nucleus. And so if we want to actually make it bigger, rather than getting energy out when we add more in, what happens is that we need to put energy in to squash them together more than it takes to get out. So fusion just stops. It suddenly stops. Things in nature don't do things that require energy unless there's energy around. And in this case, there isn't enough energy around. So eventually, the center, all fusion suddenly stops. The only force acting on it now is the gravity. Remember, with no fusion, no pushing out, all we've got is gravity. Suddenly, really suddenly, all of the outside gases that haven't fused yet come crashing down together and bounce off this really iron hard surface, and there is a massive explosion called a supernova. Now, oh look, I even put it up there. So here we are, here's our periodic table. Universe starts off with a little bit of this and loads and loads and loads of hydrogen. And the force of gravity squashes the nucleuses together until they start to bond together. So a helium and a hydrogen would make a lithium. Maybe a lithium and a helium could make a boron, and so forth and so forth and so forth for all of these. So a normal star can make all of these elements, silicon and phosphorus and chlorine and argon and potassium and all of these all the way up to iron. There it stops. So none of these elements are made in this type of star, only up to iron. And if you notice here on Earth, these are the most common elements that we find. There's loads of oxygen on Earth, there's loads of nitrogen, there's loads of carbon, there's loads of hydrogen, loads of helium. They're very, very common here on Earth. But things like gold down here and silver, they're not so common, and therefore we value them more. Going back to this supernova, we run out of hydrogen, we run out of helium to fuse together, we run out of all of the other elements up to iron. No more fusion can happen. Gravity wins. There's a massive collapse of all the gases. It bounces off the center of the star, that solid iron ball, and out is thrown all the leftover gases and atoms into the surrounding space. We call this another cloud. This is another nebula. But this time, it's not just hydrogen and helium. We've got iron, we've got boron, we've got fluorine, we've got oxygen, we've got nitrogen, we've got all of those lighter elements. And this is what we call the first generation star. So we've got now some of the building blocks that we need to make up our bodies. And that's come from this first generations of stars. So our sun is not an original sun, because if it was, all the gases around it, which make up the planets now, would just be hydrogen and helium. But that's not what we found. We know just by looking out the window or looking at ourselves in the reflection, we're not just made of those two atoms. So where did the rest come from? Well, you can imagine at the point of explosion, when all the gases collapse onto this iron ball, it's stronger than gravity. It's incredible. You've got the momentum of all the gases coming in. The pressure at that point is more immense than any gravity on its own could provide. And it's in that point that nearly all of the other elements have found, all the way up to uranium. Now, if you find uranium, it's all the way down here. So most of these here are formed in a supernova when it explodes. Now, I say most and not all, because sometimes, just like how we got beryllium from maybe a lithium and a hydrogen forming together, or we got boron from a helium and a lithium joining together, sometimes you need, like what we call the seeds. We need some of these heavier ones to help us make the even bigger ones. So this second generation star, this first generation star will make all of these, but we know, because we've got all of the other elements, that actually we're not a second generation star either. Our sun is a third generation star. So what happens? All of these gases around this supernova, the death of this first star, well, there's enough there to make hundreds of more stars. So eventually we end up with this new nebula. Now, right in the center of this one, you can just see the remains of that first generation star. It would just be a solid, it's probably collapsed in on itself. It's no longer even an iron ball. The iron ball was so big that the iron ball didn't have enough strength to fight against the gravity. And then that would have collapsed as well. It would have got even smaller. And then there'd be no spaces between the atoms and the electrons. That would have collapsed. And that's what we call a neutron star. And even if that neutron star was big enough, the neutrons and the protons themselves wouldn't have the strength to hold their shape. And gravity would have squashed that even more. And we'd end up with a black hole. And that black hole would be infinitesimally tiny, yet infinitesimally massive when it comes to the amount of matter that's in that small point. And so the gravity would again be huge, so huge that it can suck anything into it, including light. Oh, that's an interesting point. This is a true word, spaghettification. Now, I don't know if you know about spaghetti, but that's long strands of pasta. And it's true, if you get near to a black hole, if you get near enough, let's say you go in feet first, your feet are closer to the center, so they get pulled a lot more than your head does, because that's slightly further away and the gravity changes so quickly. So what happens is your legs get pulled more than your head. And of course, if your legs gets pulled more than your head, you're going to be stretched out, just like a really thin bit of spaghetti. Little interesting point there. So the star explodes in a supernova and it sprays out into space a massive amount of unused gases and material. Lots of iron, lots of oxygen, nitrogen, the works. It all comes out, and even some of the heavy elements that were formed in that massive explosion. Oh, look, I even got some pictures. So the dense core, this is what's left over, the core in its center. Again, the iron was too much. It collapsed in on itself. And so it was just a massive ball of hydrogen, not even hydrogen, massive ball of protons and neutrons, which then itself could collapse and form this black hole. That's quite interesting. A neutron star so dense that 1 teaspoonful, that's a tiny thing that you stir your tea with, would weigh 100 million tons. Just incredible. Now, you can't see a black hole, so how come I've got an image here of a black hole? Well, the very center is the core of the black hole. That's the bit you can't see, that's why it's black. But round the outside, as the light comes in, it speeds up and speeds up and speeds up, and any gases that are there speed up and speed up, and they get so fast that when they crash into each other, they get hot and give out light. So we can see what was called the event horizon around the outside edge of the black hole before that itself is sucked in, never to be seen again. Right, come on. So, nope, that's not the end. That's only the end of that star. We can make another star from the leftover gases up here. Let's have a look. The leftover gases that are left over, these can create new stars, a new nebula, a new cloud, this time not just hydrogen and helium, but elements as well, a whole mix of elements. So, as I said, our star is at least a 3rd generation. So there's been 2 more stars before it, all of them producing the elements that we have here on Earth. Now, it's not blue anymore. It's not that big. It's a fairly boring, bog standard size of star. Many stars are much bigger, many stars are much smaller. It's just hot enough so that it gives out mostly yellow light. So to us, it looks pretty yellow. If it was a bit smaller, there'd be less fusion because there's less gravity. So it might look a bit redder. And if it was a bit bigger, maybe it might look bright white, something like that. It only starts looking blue when you're getting more kind of ultraviolet and violet colors than you're getting of the reds, which is incredibly hot and very, very large. So I could literally roll back and start again. We go all the way back up to here. At the moment, our sun, as it comes, go back here, our sun was started in one of these, but this is not a cloud now of hydrogen and helium from the Big Bang. This is a cloud of dust and gas from those 1st and 2nd generation stars. That's what's left over from them. And gravity again comes along and pulls it down together, and it creates these first types, this first stage of the star, the proton star, where we get the spinning from the whirlpool effect as water goes down. And the center starts to glow, the gravity gets really strong again, and we get finally fusion happening where what left over helium starts to fuse, and we get our sun finally starting to glow. Now, just like all the other stars, not all of the gas and particles get drawn in. We're left with some that end up just spinning around the sun, just as the gas particles are left over in other places. Now, it's not just gas anymore, remember, we've got all of the elements. And so gravity brings them together, the particles coalesce, that means come together and stick, and we start to get the different planets. And we are right here, and we're in what we call of the Goldilocks zone, which means it's not too hot and it's not too cold. In England, we've got a story all about a girl who goes to visit some bears and steals their porridge, their food. And she doesn't like the really hottest one, and she doesn't like the really coldest one. She likes the one which is just in the middle. And so we've come up with this name called the Goldilocks zone. That's named after the character in this book. So Mercury and Venus are really close, and they move around the sun really, really quickly, and they're really, really hot. No life can live there. And if we go out to Mars, well, actually that's pretty chilly out there. They've got snow caps of frozen carbon dioxide at their poles. Pretty chilly. I mean, most of the time we're talking -40 and worse. And then further out again and again, it gets colder and colder and colder. But we're very lucky. We have been left over here, left in this perfect spot where water can exist. Not only water, but we get ice and we get water vapor or steam. It's quite an incredibly lucky spot to be. But that's why we developed there, nowhere else. So it's absolutely true. If someone says you're gold dust, or sorry, not gold dust, if you're made of stardust, that's absolutely true. We have been made up of the leftover particles from the stars before our own. What's going to happen to our sun? Well, eventually, like the suns before, it's going to run out of hydrogen. All that hydrogen will have been fused together. There'll be lots of helium around. And so at the point, then the helium can't fuse at that size, so gravity will suddenly squash the core until it's enough pressure again for helium to fuse, and the core itself of our sun will shrink to about the same size of our Earth, so really millions of times smaller. But as it does that, the outer gases will expand and be released from the center, and they'll get so big that it will actually come and envelop our Earth. So we're history at that point. We've got a few more billion years to go yet, so no reason to get worried. But that's what eventually was going to happen. Right, so after that, you're going to be, all the gases are going to float off, and you're going to be left with this white hot iron ball. Now, this time we didn't have a supernova because there wasn't enough gravity to bring all of those gases, once fusion has stopped, rushing back in again with enough force to cause more fusion. So we're just left over with a white hot ball of iron that will stay again there for millions, if not billions of years, giving out a tiny faint amount of light before it just gets cold and turns off. And that will be the end of our sun. Really, right down there will be this black, almost impossible to detect, dense area of iron. Won't give out any light, so we won't be able to see it. Aliens out there in the universe will have a look, but won't see anything. All right? And that's the end. But if we look down here, just to sum it all up, I've got a picture of the different stages that one star goes through. We start off with this nebula, a mix of dust and gases. And if it's small, we go down this route. And this is the way our star has gone. Before, the first stars were much, much bigger. So they turned into the bright blue, massive stars, and then went into super red giants, and then collapsed into supernovas, and then were left as neutron stars or black holes. And the dust from all of these that was left over after the supernova went back and started a new one, which then went to another one of these. And then the gas left over from that started the creation of our star. So we're the remnants of all of these different things. Our star is here. We're about halfway through this stage. Give it another 4.5 billion years or so, our sun will expand and kill us all. And we'll be left over with this white dwarf, a white hot ball of iron. So that's really the end of my lecture. So the only way that we're going to keep ourselves entertained is if you ask some decent questions or get me to talk about what life's at CATS Cambridge, what life's like in Europe, or if you're interested in the stars, I can talk a little bit more about that. I see someone has asked me how the epidemic is going in the UK. It's early days for us. We've only just been put in home quarantine since Friday. So we're all just getting used to staying at home. We're only allowed out to buy food or to have one bit of exercise a day. We've got to stay 2 meters away from everyone. And that's it, unless we need to go to hospital or something like that. We've still only had about 400 people die so far. but the government is really worried, and they're doing everything they can to slow down the spread. I don't think they're going to stop it. They're not going to try and do that. What they're trying to do is make it kind of not peak, not all come together at the same time, so that the health service can keep looking after us, and there's always a doctor available for the very sickest. So probably will be like this for at least another 12 months, I imagine. Will be very hard. Are there any other questions about anything at all? If you come to England, you have to ask questions. You get in trouble if you don't ask questions. Ah, someone earlier put chemistry, question mark. Yeah, physics and chemistry, you know, they're not that different. We're all looking at what the Earth and the world is made up of. So eventually they cross over. Physics generally just looks at the nucleuses when it comes to looking at materials. So we call that nuclear physics. Whereas the chemists tend to look at how the electrons are arranged and how the electrons interact with each other. Physics likes to think that we teach the chemists everything they know, but it's not true. They learn a lot more stuff that we don't know. So is anyone here going to become a doctor or want to carry their physics on at university? Ah, good question. Will the Earth disappear? Well, hopefully you've been told nothing actually disappears. The Earth will get burnt. So the heat from the sun, it will burn all of the organic matter. So, you know, there won't be any carbon left. It will turn into carbon dioxide, and that will evaporate and actually probably turn into a plasma. So yeah, there'll probably be a lump of kind of charred bits of carbon and rock left over floating around in space for the rest of time. Or you never know, it might, lots of stardust or our whole solar system might be drawn into another bigger group of stars, which then collide and maybe start a new star, and our bits will make up the next elements for the next solar system that comes after us. Okay, so could you please explain again how those metal elements are formed? Right, so let's go back to how this happens here. So this is the simplest one. So here is, remember that this is just a heavy type of hydrogen, one with an extra neutron. And this is a heavy type of hydrogen with 2 neutrons. They don't want to come together because they're both positively charged. So naturally, we can't make hydrogen fuse into helium here on Earth. We don't have enough pressure, we don't have enough temperature. Now, we're working on it. If you've ever heard about nuclear fusion reactors, that's what we're trying to do, because when it does, it releases lots of energy. So these two, they have to be under incredible pressure. And then when they're squashed together, they finally stick, and what's called a strong nuclear force takes over. And that's like the stickiness on the surface, which means if they touch, they bond together. And when they bond together, that's a really, really strong bond, and they won't break apart. So when we look at the elements further down, like up here, let's see if I can do some drawing here. Yeah, hopefully, pen, draw. Let's see if I can do a wiggly right. Right, so let's say we've got, let's have a look at carbon. So carbon would be 1, 2, 3, 4, 5, 6 protons, and then it would have maybe some neutrons. 1, 2, 3, 4, 5, 6. So I'm going to put pluses in some of them. That's the protons. 1, 2, 3, 4, 5, 6. So I'm just looking at the nucleus. I'm not going to be bothered with the electrons. And you get 2 of these, and these really don't want to come together because they've got 6 pluses coming together with another 6 pluses. That's really difficult to do. So this only happens when the star is collapsing. It's in the red, super red giant phase. And when these two come together, when you get a nucleus, which has now got 12 protons in. So we have to go, well, that's 6, 7, 8, 9, 10, 11, 12. So that's how we form magnesium. And that's exactly the same what happens again. If we join two magnesiums together, we would get chromium, right? And then if the chromium bounced around and hit, say, a helium, then we'd end up with our iron. It's just at that point, no more energy is released. So the temperature immediately starts to drop. And so there's not enough temperature, i.e. enough speed of these particles moving around for them to hit with enough force to overcome that repulsion. So they'll come in, but not quite fast enough, and they'll go, ugh, and then move apart again, because they're both positively charged. I hope that helps. Ask again if you want to. Right. Can we know how many stars altogether in the universe? Right. You got the right idea. There's galaxies in the universe. And they did an experiment where they basically got a telescope in space and they pointed it at what they thought was empty space. And they, like a camera, you know, if you leave the lens open for a long time, it gathers lots and lots and lots of light. Well, they left it open for about a week, pointed at this place. Now, get your smallest coin that you have and hold it at arm's distance. So it's like this, right out there. The coin itself would be about how much space. Actually, it'd be smaller than that. Think of a full stop. Hold a full stop at arm's length away and hold that up. That's how much space it was looking at. And they left it open for a whole week. And then after that, they developed the camera. Now, normally you can't see anything in that space because it's just dark. Our eyes aren't sensitive enough. But when they developed that picture, they found within that, there was thousands and thousands and thousands of galaxies. And when I say a galaxy can contain hundreds of billions of stars. And so they did the maths. They said, well, if this tiny little space that we've looked at contains hundreds of millions of galaxies, then let's have a look. Let's see how many of those little spaces there would be if we looked at all in all directions. And they multiplied that up, and that's how they come up with an estimate. So no, we don't know exactly how many there are, but we've done that kind of surveying where we look at a small area, and then that gets, we do the maths and we turn it into a really large number. So it is hundreds of billions of stars. Cool. Right, what's my favorite sci-fi movie about space? I don't know if you've seen it. It's called Blade Runner. And it's a sci-fi movie about the future where they make kind of human-looking like robots to work on distant planets to like do farming and things like that. And these robots start to get a sense of who they are. So they kind of become self-aware. And they try to get back to Earth to find who made them. And it's a story about how there are some humans who are sent to make sure that they don't come back. And they do, and it's all kind of makes you think about what's the purpose of life and that kind of stuff. Right. What's the furthest nebula we can see right now? Or the furthest star? Yeah, you can't really see nebula, because we only can detect them by seeing the light and how the light travels through them. So there's got to be stars behind them. So yeah, a nebula is literally like all of the material that makes up a star, but is so spread out, you know, gravity hasn't brought it back together again yet. You're waiting for gravity to bring that together and to cause it to heat up and to have enough kind of pressure and temperature to start fusing together. So the furthest one away is, well, we kind of measure it in light years. So light travels very, very fast. It travels at, you know, 300 million meters every second. So if you do the maths, we can work out how far it would travel in a year. You know, you do what? How many seconds in a minute? 60. How many minutes in an hour? Etc. 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 Until you got to how many minutes, how many seconds in a day, and then how many seconds in a year. And then we work out, we times that by how far it goes every second, and you get this massive number, and we call that light years. So light years isn't really a time anymore, it's a distance. But the universe is also we know how old the universe is, because you know how I said the universe is expanding? Well, as the universe expands, everything moves apart from each other, and we can measure how fast things are moving apart from each other. And that we can say, looking at the furthest away we can see, is 13.5 billion light years away. So we know that the whole of the universe is 13.5-ish billion light years old, which is the same as far as we can see. How asteroids are formed? Well, they're literally just the bits of material that were blown out into space after the star exploded, and they've convalesced together. So they've been brought together by gravity. And they're asteroids. You know, we've got an asteroid belt just outside of Mars. Well, that asteroid belt are really all of the bits of material that should have formed another planet, but for some reason they didn't all come together. Does physics have any links to economics? Well, put it this way, in England, if you get a physics degree, anyone in banking or economics thinks you've got a brilliantly big and clever brain, and you can really help them make lots of money. So I suppose the maths that developed in physics might well help in economics, and you'll certainly be able to get a really good job in economics if you've got a kind of degree, so especially if you come to the UK. Could the entire universe be a lab for an advanced civilization we don't know about? Well, I mean, to be honest, there's no evidence for it. And, you know, this is how scientists work, is that they look for the evidence. They look, have they left behind some litter? Have they left some sweetie packets around that we can see? And there's no evidence at all that we're being controlled. We obey the simple laws of physics. Those laws apply everywhere in the universe. And you might think, oh, how on earth do you know that, you know, the laws apply everywhere? I mean, how do we know that on the periodic table that are all the elements out there? But we can, and it's by scientific measurement. If you look at a star deep out into space, the colours come from the star have got little black lines in them where no colour comes. And that's because there's gases in the way. And those gases, like, you know, sodium lamps, I don't know if you, orange street lights. In England, we've got orange street lights that give out a certain colour. Now, that colour never comes from the sun because there's helium in the sun's atmosphere, which absorbs those colours, the same ones that give out when light comes from that particular gas. So we know exactly what elements there are out there in space. So I don't know about other advanced civilizations. It's possible, but we've got no evidence for it. Cool. Has anyone else got any other questions? Is there anyone here who would like to go on and do physics, or is anyone here likely to come over and visit us in Cambridge? Well, it depends how far you want to take your physics when it comes to maths. My maths is not amazing. I certainly wouldn't be able to do a maths degree right now. I mean, I probably would just about pass my physics, my maths A level. So it doesn't have to be amazing. The maths that required at physics for A level, I reckon from what my experience is with Chinese pupils coming over, even at GCSE, you've got enough, even when you're 16, you've got enough math skill to be able to do everything that you need to at A level. So yeah, don't worry about that. If you want to go on to degree, then it's pretty important that you can differentiate and integrate and do some of the harder maths. But you know, they'll teach you there. They'll teach you. So don't worry if you think that you're a bit weak on the old maths front. You've got time, and I can assure you that all the students I've come across from China have been amazing at maths. Okay, any other questions? We've still got about 8 minutes, so if you want to ask anything, go for it. This is your chance. Is physics compulsory for medicine? No, no. I think chemistry is definitely compulsory, and I think most people do biology. Physics is becoming more and more important in medicine. If you think about X-rays, that's a very early part of medicine that needed physics and physicists. But now we're doing radiotherapy, which is the treatment of cancer with gamma rays and gamma rays and alpha particles and beta particles. So it depends what particular type and area you want to get into. Certainly, if you want to treat people with cancer, I would have said, having a basic understanding of physics is really important. I know from a friend of mine who's a dentist. She's one of the top dentists in the country, and she goes around and has to teach now doctors and things about how X-ray machines work. So, yeah, again, it's not going to stop you. You're probably going to look a bit better than others who haven't done it. So it might be a good idea if you're thinking about it. Certainly chemistry, probably biology, and then you've got a little bit of flexibility. If we choose physics, which subjects can you choose at university? Right, if you're talking about A-level, then physics basically gives you access to anything to do with engineering. So that kind of thing. It also gives you, physics is one of those things where it's more a proof that you've got an amazing brain and that you can work out difficult problems and think about things which aren't obvious and straightforward in front of you. So it's a really good qualification to have in that respect. And it does train you to think very critically. So most people are pretty impressed with the people who have who studied physics, and they can go on to most subjects at university. Of course, if you want to do English language or if you want to do Chinese history, you want to make sure that you've got some other things as well. Is it very difficult to study physics at high school? I don't think so. I would say pretty much that the level of physics, those who choose it and work hard, most of them will get a B, an A, or something along those lines. So it's not impossible by any stretch of the imagination. Good. Any other questions? If you do come over, it'd be delightful for you to pop in and say what you thought of the video. This is the first time I've done this, so it's been a bit nerve-wracking, and I'm sure there's lots of ways I can improve. So yeah, do feel free if afterwards you talk to anyone that get a message to me, and I'll find that really interesting. Right, I'm not quite sure from Tom what you mean by that one. How much hard we need? Try and put it a different way, and I'll try and answer you again. Oh, the Milky Way. Okay. So I've got a message saying, please could you talk about the Milky Way. Well, the Milky Way is just an area in space where it's a galaxy, just like lots of other galaxies we can see, and it's a collection of billions and billions of stars, and we're just one of them, on a fairly insignificant one on the near the outside edge. Yeah, that's it really. There's a lot of repetition in space, and stars are very much a repetition of one another. It all changes slightly when we look about the details, but pretty much one star has a very similar characteristics to the next, and it only depends on its size, how we see it and what it's like to be around. So Tom's clarified a bit. How hard do we need to study for physics? In England, the way it goes is that all the A levels, whether it's in English, maths, chemistry, history, they're all meant to be just as demanding as each other. So if you're good at one of those subjects, you're naturally going to find it easier. But it's not like physics is much harder than any of the other A-level subjects. A-levels are demanding. To be honest, the amount of pressure you're under at A-level is as significant as it is at university. But it's one of those things, if you're self-disciplined, you do a bit of work when you're asked to every day, then, you know, most people get really good grades. It's only those who decide, oh, I can leave it to the last minute, or don't have the kind of strength of character just to keep going, even though they're finding it hard, they're the ones who will struggle. So it's not any harder or any easier than any other A-level. They're all meant to be the same. But don't do it if you hate the subject, because that's crazy. You want to do something that you love, because you're going to be spending quite a lot of time doing it. Right, I think that's pretty much the end. I've got time if you want any last questions. Otherwise, thank you very much again. It's been lovely having an audience, and thank you very much for those who are brave enough to put a question in. I hope I haven't spoken too fast or made it hard for you to understand. Normally, I would cover this in about, I would say, going over it and practicing a couple of weeks would normally take for us to fully develop the kind of understanding that you need, so that you can get to the point where you can basically talk about the stars as I have. So yeah, don't be concerned if it was all a bit much and a bit fast. So thank you again.
Thank you very much, Douglas. No homework?
No homework? Well, no, I don't think you need homework.
Thank you so
I mean, have a look at those slides. I would love to have more questions, and I'd be happy to email you any answers if you've got them, if you need them.
Sure. Thank you so much. Much appreciated.
Pleasure, pleasure, pleasure.
Thank you. And that's all for today.